Give you an introduction, then you can start. Okay.
All right, so we'll start right now. So at first, thanks for everyone's coming. And today, I will define my dissertation in the title of Statistical Bayesian Inversion of Directional Electromagnetic Logging Data. And for a brief outline of this presentation, I will cover the introduction and the major parts, the methodology, and our future works. But finally, I will summarize the topic of my dissertation. In detail, the introduction part will cover our research background and our dissertation scope, which motivate us, the challenges which motivate us and push us to contribute of our works. And the second part is the major body. We will cover the Bayesian theorem, the Bayesian statistical inversion, and we will illustrate such ideas through several aspects of several methodologies, including the traditional, the classical Bayesian inversion, the theorem, and the hybrid scheme, or the self-parameterizing scheme, as well as the tempering method. And our future works will drop in these three major categories, including the hierarchical Bayesian modeling and the 2D inverse modeling, as well as the deep learning or assisted statistical inversion. And lastly, we will draw the conclusion. So, the introduction. We're working behind the well logging, the background of well logging, which is a practice of making a detailed record of geological formations like the physics of the rocks or the lithologies. So there are multiple types of logging sensing systems, including the gamma ray, the resistivity, the neutron porosity, or many others. Beyond this, the logging well drilling technique, which convey the well logs practice, and during the well logging and transmit the data back to the surface, sometimes for the real-time decision-making purpose. Our topic was behind the one particular service named the Directional Electromagnetic Logging Well Drilling Service. It covers a few concepts. The first is the directional drilling, which is a practice of controlling the direction as well as the deviation of the well bore, as well as the electromagnetic sensing system, which adopt the physics of the EM and which transmit the antennas propagate the EM waves into the earth formation, and the receiver captures the EM signal and record the change which influenced by the surrounding environment. So combine these two concepts, the directional EM logging well drilling service is a practice which to understand the Earth's electrical properties. It's best used for the distinguish of the conductive formation like the salt water and the resistive hydrocarbons like the oil and gas. So the tool we use for such a service, we name this directional resistivity logging well drilling tools. It consists of the tiered antennas, which provide the directionality, the sensitivity of directionality, and there are multiple pairs of transmitter and receivers working behind the different frequencies and transmitter-receiver spacings. By adopting the concept described before, one of our most popular tool today is introduced a few years ago. We named it the ultra-deep directional resistivity logging well drilling tool. Within a few years, the type of tools are greatly enhanced with a much larger detecting range. Such type of tool can extend the depth of investigation over 100 feet from the borehole location. Such kind of service, the ultra-deep tools makes the broad range of service possible. To implement a reliable service, there are multiple service applications we can achieve, such as the geo-stopping, which avoid driving handset and landing a target zone, landing a well, as well as the geo-steering, and which maintains the tool in the target zones and maximize the production, and avoid drilling breakthrough the well. And a new concept during these years we call the geomapping, which identify the extent and the shape of the reservoir, because due to the large depth of investigation. To implement a reliable service with maximal performance, the logging data interpretation is one key step. So before we go to the challenges, we need some definitions towards our workflow as well as the EM logging data interpretation. So we define the problem here as a 1D problem, which we parameterized our problem into a layered model, and in which layer it has a constant physical properties. We need a forward modeling based on this 1D parameterization, and which solves the Maxwell equations to answer the projection from the model parameter to the signal response. Our target here behind this topic is the inverse modeling, which determines a certain Earth model which reproduce the EM response as the answer of forward modeling as measured. To define our objective, what is the inverse modeling and how to interpret the ultra-deep logging data? We have some notations here, and we will keep this notation in the following presentation. And first, we define the D as a vector of EM logging well drilling data, and the M is the vector of Earth model parameters. Behind the physics of the electromagnetic, we define the electrical properties of the formation, like as the vector of resistivity value, as well as in the model-based inversion, we define the vector of Z as a vector of depth of layer interfaces. And we need a forward modeling here, F, the function that calculates the EM response given an Earth model. The problem objective, the ultimate objective is given a EM measurement data, we need to find the Earth model M, or the distribution of its parameter. We will talk about this later, where a certain model which can minimize the data misfit between the forward response and the observation. So now we have our objective. We are facing some challenges behind this. The first challenge is the nonlinearity. Here, assume we have an ultra-deep sensitivity, which introduces a very large depth of investigation. Here we have a picture which is a 2D resistivity profile. It was grouped by multiple logging stations, the result of multiple 1D results. And we group each 1D result into this 2D profile. With a larger depth of investigation, the scope of the tool or the evaluation zone, the reservoir, becomes larger. And more Earth geological features are within the scope. The Earth model to be inverted becomes complicated, as well as the response of EM tools, the ultra-deep tools, because the formations we evaluate becomes much complex. So the inverse modeling is very complicated, while the problem is highly nonlinear and highly dimensional. So there are many local minima. That's it, which is the problem we need to conquer in the future. The second challenge is the model selection problem. As we defined in the 1D parameterization, the layered model requires us to define the number of layers which can best represent the model we want to infer. But a predefined number of layers may cause a model under-parameterized, which the number of layers cannot represent the true scenario or over-parameterized, like we use more number of layers to describe a simple case. So there are another scheme we call the pixel-based inversion, which discretizes the entire space we want to evaluate into equally thickness layers. There are only one target we want to infer, we want to know, is the resistivity of each thin layer. But the problem sometimes becomes underdetermined because maybe the number of parameters would be larger than the measurements. So a regularization term must be applied to the problem. But sometimes the human assumed the pre-assumed regularization may cause the low resolution or some bias from the truth. So when we return back to the model-based inversion, we still need to determine how many layers we need. So maybe a new method should be proposed which can self-parameterizing the model and to answer how many layers we need through the measurement itself. The third challenge is the efficiency. There is a workflow of directional logging while drilling. Sometimes it's an alternative way, alternating the two steps one by one. The logging tool record the measurement at real time, and it feeds back the drilling data to the workstation or to the service and do the real-time data interpretation. And the result will turn back as well for the guidance to help navigate the tool and for the decision-making purpose to direct the direction of the logging path, the well bore path, the well trajectories. So a prompt formation evaluation workflow is in need for decision-making, especially in the real-time scenario. So to brief summarize our dissertation contributions, we are motivated through those three challenges, and here they are made through the several thrusts of this contribution. The first thrust is we propose the use of statistical inverse methods that interprets ultra-deep EM logging data, and we use the statistical Bayesian inference here. The second thrust is we handle the self-parameterizing problem and to infer the model complexity by using the transdimensional Markov chain multicolor method. For the problem of efficiency, we proposed two very effective ways to handle this. Through the hybrid sampling scheme as well as the tempering scheme, which by using the parallel tempering technique and enhance the sampling speed, adopting the high-performance computing platform. Okay, so now we will jump to the next section about the methodology, what we use the statistical inversion. At the first chapter, we will talk about the basis of the Bayesian inference and the sampling method, how to build a sampling scheme to draw the sample of our target. The Bayesian theorem describes the probability theorem behind the statistics, and it describes the probability of an event based on the prior knowledge of conditions that might be related to these events. Just for example, if lung cancer is related to smoking, then using the Bayesian theorem, a smoker can be used to more accurately assess the probability that if the person has a lung cancer compared to the assessment of the probability of the cancer made without knowledge, because it's the prior knowledge of the person's smoking behavior. We call this probability as a conditional probability. So the Bayesian equations connect the two events here through the equation here. the events A and B. So what is the Bayesian inference? It is a method of statistical inference in which the Bayesian theorem is used to update the probability of a hypothesis as more evidence of information becomes available. Here it gives a relationship between the hypothesis here, the humans, the target we want to know, and the evidence we have, the observations here. We use the same notation M and D accommodating into our problem here. The M is the target model we want to infer, and the D is the measurement we have, which is the evidence here. So given the measurement curves here, infer the posterior probability through the inference of the likelihood and the prior knowledge towards this word. And here the evidence is marginalized over the parameter space, so it will remain the same for all possible hypotheses when we have a trial. So the Bayesian inference usually is defined into the relationship between the posterior and the prior and the likelihood. More specifically in our problem, the likelihood probability P is given a model parameter that we describe the measurement following a certain statistics. It depends on the noise type, and we have a more detailed form of this likelihood function. The likelihood function measures the goodness of fit through this Gaussian shape, Gaussian form. And here, the goodness of fit is exactly like the target we want to know, that the data misfit between the measurements and the forward response. We want to find the best model that match the observations, which can maximize these likelihood functions. And with this, we define these statistics according to this Gaussian form, which represent its noise we defined. The prior probability, PM, which estimate the Earth model before we have the observations, before we take the measurements, it's usually taken as the prior knowledges and as well as the regularization, which constrain the model parameters within a certain range. For a brief example here in our problem, our target is the resistivity of each layers in the layered model. The layer's resistivity is one target, as well as the interface, the location of each interface. So we may use such unbiased or broad range of this prior knowledge to constrain it as a certain range, the upper and the lower boundaries. So the next we want to introduce the Markov chain multicolor method. We know the relationship between the posterior and the likelihood as well as the prior, but how to know how this posterior distribution, what's its shape, what's its statistical informations, properties like the mean value, mode, range, variance, that how these parameters will be distributed and what are these statistical properties. We need a sampling method. So here the MCMC method would be a very good companion with the Bayesian inference technique. So the MCMC method is a class of algorithms that sample from a posterior distribution by constructing a Markov chain whose invariant distribution, which will be exactly the same as the posterior distribution. But there is a connection between the chain distribution and the posterior distribution that the question raised is how to construct such a Markov chain whose distribution has such a property and can represent the posterior we want to know. before going that, we have some a little bit background of the Markov chains, which is a random process, a stochastic process, and we draw a sequence of random samples along the time series. The Markov process defined asks that the probability of the nth event only on the state attained depends only on the state of its previous event of n-1. So we call this transition, this form as the transition kernel that described how the transition changes along the time. The state of this chain changed along the time sequence. We still need to define the probability here, the Markov chain's probability, which is a probability distributed over the state at a time t, at a certain time. So we need to define what is the stationary, which is invariant along the time. And it requires that the system does not have only one state, but a distribution over the states. As well, this state will not change along the time. So our target is adopting these invariant Markov distributions, and we construct such a chain using a certain method who has a probability distribution over the states, and this distribution is exactly as the posterior or the target distribution we want to know. So beyond this, there is one good property that Markov chains can be proven that is stationary and invariant along the time. So we call this property as a reversible, and we call this chain is reversible, and it satisfies the detailed balance, which is the sufficient condition that the chain's distribution is a stationary distribution. Here we gave a very brief proof of that how these schemes could satisfy this condition. The transition of chain's distribution from the current state from the next state equals to its reverse transition. That's the requirement. And we did a proof that we transit reversibly in this form, and we take a summarize of these two terms. And here we can see the transition from the state to the all other states. The summary of this probability could equals to 1. So we got these conditions here. We call it the reversibility, or satisfy the detailed balance condition. So how to construct such a transition kernel that satisfies this condition? We have a very best tool to achieve the MCMC method. We name it the Metropolis-Hastings algorithm, the very classical sampling algorithms here. This is a method that generates a sequence of random samples from a certain probability distribution iteratively. It's a accommodates the idea of Markov chains, and by constructing transition kernel through we call this probability named Metropolis-Hastings acceptance rules. It has been proven that here, as according to these rules, the samples generated satisfy the detailed balance. So behind this, it compels the candidates, the probability of candidate, as well as the probability of current state. The one good property is here, it cancels the terms of evidence. So we don't need to calculate the integration of these marginalized distributions, but only compare the likelihood functions and the trial functions. And each time we have a randomly generated new models here through Gaussian distributions. We call this the random work. And for the sake of this proposal, it introduced the randomness into the algorithms, and which may conquer the local minima problem by adopting this stochastic process. And we have one simple examples that to interpret the logging data and to reconstruct the 2D Earth model profiles. Here is a true synthetic models with 120 logging points. We conduct Bayesian inference using the random walk MCMC method at each logging point, and we gather a group of samples, and we use the mean value of those samples to reflect our inverse result, and we use the variance of those samples to reflect the uncertainty of this result. And from these very easy examples, we can see the using of the statistical Bayesian inversion helps to conquer, in some way, to conquer the local minima through the statistical stochastic process by introducing the randomness into the interpretations mechanism. And we can also assess the uncertainties. But problem is very obvious because the random work, the sampling scheme is very low efficient, and it cannot fulfill the requirement of the real-time logging, real-time interpretation. So the next sections, we will introduce hybrid schemes that combine the deterministic ways with the statistical sampling methods using the Hamiltonian dynamics. Like I said, we are motivated by the real job, and which ask that the statistical samplings conquer such a local minima problem, but with a very low efficiencies due to the random walk properties. So the combination of the gradient-based method with samplings may bring some help. Here, the hybrid Monte Carlo, we name it as a gradient-drifted sampling method. It simulates by simulating a Hamiltonian dynamic system and the candidate follow a gradient drift. It boosts the sampling speed quite much. And so firstly, we need to introduce the Hamiltonian dynamics, which describes the particle movement in a system. The scientists are very brilliant because they adopt the ideas from other domains that when they observe some certain behaviors in their domain and combine these ideas with other, like with the statistics, it becomes very interesting. So briefly to introduce the Hamiltonian system is describe the motions of a group of objects. It starts from the particles in a microspace. Group of objects in terms of its location and momentum is more like a physics. We have learned in our high school that Newton's theorem governs theory. We describe the system using a vector of location and its momentum at a certain time t. So for each location, it is associated with a potential energy. And for each momentum, the particle is associated with kinetic energy, K of P. We still adopt the same notation here, M, and the P will introduce this as auxiliary variable. The Hamiltonian function defines a total function, describe the total function of this entire system using the combination of potential energy and the kinetic energy. That's the total energy of this system. And Hamiltonian equations by using two equations which to describe the change between times along the times. It describes the conversion between the potential and the kinetic energy, its transformation one to each other. So the Hamiltonian dynamics describes such a system. So what we can learn from these equations we described before. Given the expression of such a change, the transformation between the energies, and a set of initial conditions at a certain time t0s, like the initial position of each object and the initial momentum at a certain time t0, we can predict the location and momentum of a system at any time point after starting. So here's one example which describes a physical system here, the movement of the ball. And we use these two bars to describe the total energies, and here we describe the position of this ball. We can see it's almost preserved the total energy along the time, along the change, but there's still a minor difference. That is due to the discretization, because the Hamiltonian dynamics describe the system in a continuous space. So we need to approximate these Hamiltonian equations in a discrete time space. Here we use the leapfrog method that alternatively update the particle's properties, its position as well as its momentum. Here, the sigma introduced is the discretizing step size, which help to achieve the simulation of this Hamiltonian dynamics. How to introduce the Hamiltonian dynamics into the sampling scheme? That's the idea raised, and it is the brilliant that we combine the physics with the statistics. So we introduced the hybrid Monte Carlo. We need some definition that accommodate those variables and energy forms into the sampling space and objective function. A very easy bridge that to combine these two parts is like we defined before. We use the U of M, the energy function of model M, just like as our objective. So this term is our objective function. And the K of P, the energy function, the kinetic energy, we introduce it by artificially introduce an auxiliary random variable P, which follows a very simple statistics. And we construct such a kinetic energy through its original form just to accommodate the Hamiltonian dynamic into the statistical sampling form. A very interesting bridge here, which connect the energy function with probability density functions. We use such an equation. This is a very good properties, and we'll introduce such connection in the later chapter. It's a way that to describe one single optimization problem and its comparing counterpart and its probability density functions. There's a way that to connect them through this form, and we will talk about this in the later chapter. So the Hamiltonian sampling is very easy following the random walk Metropolis-Hastings algorithms. We started from the current sample, but no longer for random walk. We follow this Hamiltonian dynamics. We use leapfrog simulation to follow the Hamiltonian dynamics to generate a new candidate. Such a new candidate follows such a dynamic, so it follows a gradient drift to a better finding a local, finding locations that need to sample instead of random work along the distribution space. You still need to go through the Metropolis-Hastings acceptance rule to guarantee the samples the chains we constructed by the samples to be invariant, which satisfy the reversible or the detailed balance condition. So a new sample is accepted or rejected through the Metropolis-Hastings way, and we gather a group of samples and using those samples to reflect the distribution or the statistical properties. A good way to compare the hybrid scheme and the random walk scheme, we can see the trace plot And here we use the model misfit that the current sample in the true model in a synthetic synthetic example here. We know the true model and we compare its difference between the sample and the true model. And we draw such a trace plot. And here we use logarithm scale in the x-axis. And here we can see the convergence rate, the convergence speed of hybrid scheme is 1 magnitude faster than the random work. And here, the obvious assertion is that the grading information introduced drifts the samplers for better sampling of this region in the target. And while the acceptance rate is much higher than random work, the optimal random work acceptance rate is around 0.2, which means that 10 samples, we can only accept 2 samples and reject all the remainings. But the hybrid schemes boost such a sampling speed and make the sampling more efficient. So that's the reason we adopt the hybrid Monte Carlo to do the sampling work. And it is a comparison between the pure deterministic method. Here we use the Levenberg-Marcos algorithm and one optimization way to deal with the optimization problem. And this example consists of around 50 logging points. And we do the inversion and we do the interpretation at each logging point. The first figure shows the true 5-layer model, and the middle one, by using the original optimization method, shows the result here. And this is the result combining the sampling method, the hybrid Monte Carlo, and we obtain the inverse result through the mean value of those samples. And we added one more. We refined this result by using optimization method. We get a very higher quality compared with the pure deterministic method. So the next section, we move on to the self-parameterizing problem, which we stress is our second stress. And we want to handle the model complexity interpretation. We want to know how many layers could be defined. Just to recall in the introduction, the tool provided very rich but complex information. But how many layers we need to use to define this problem and to put it into the inverse modeling process? This 3-layer model, 7-layer model. So the problem becomes harder to solve when even the assumption of the Earth model is uncertain. We record the form of Bayesian inference here. It describes the relationship between the posterior and likelihood and prior. We make some little change here. The transdimensional way, we refine these Bayesian equations, and it's a generalized one. Here now, the type of model or the number of layers here, K, becomes an unknown parameter to which we want to sample. Thus, the original idea is come from the Green's paper in the 1995 and 2003. He called this name is the reversible jump MCMC, which is a generalization of the traditional MCMC method. So now the model complexity, the model dimension is not a fixed value but a random variable. It by adopting the idea that we need to construct a Markov chains. By constructing a Markov chains with a stationary distribution across the model dimensions. So the sampler now gain the ability to sample the Earth model parameters across different dimensions. Oh, sorry. Okay. To briefly introduce the reversible jump MCMC method, according to Green's paper, it describes defined a new transformation form here from one single space to another single space, and its reversible form from the space to its original space. Here we use a very abstract function here, the dimension, to describe this transformation here. We introduce a new random variable here, the u here, which to fulfill the conditions that according to the transformation, it preserves the volume or it preserves the dimensionality between the transformation. But it's very abstractive term. So the function h is also a very abstractive way to describe the transformation. And here is only one requirement that such a transformation between the dimensions exists and be differentiable. Green shows that to maintain the detailed balance, the Metropolis-Hastings acceptance rule should be updated a little bit here, adding one term. The determinant of the Jacobian of this transformation. It is very abstractive. So here the determinant of the Jacobian of this transformation forms guarantees that the samples we accept satisfy the detailed balance. But such kind of abstractive terms is very hard to numerically calculate it. So we need one more analytical solution to deal with such kind of problem. We call it a birth and death simulation. In a layered model, it is a process that to achieve the reversible jump according to such an analytical simulation. So give a brief example. We give a two-layer model here with one interface. There are two types of moves. The first type is the birth move, which increases the number of dimensions and insert an artificial interface at a random depth. It perturbs one model parameters in the newborn layer. The other way to achieve its reversible form, we call it the death move, and it selects an existing interface randomly and remove it. And we merge two neighboring layers together. It's a very simple process. But according to birth and death simulations, it guarantees the Green-defined transformation between different dimensions. And the whole scheme of this transdimensional MCMC samplings proposes three different steps. And from the initial model, we still need to generate a series of random samples. But the proposal steps will follow the three different steps. Like we introduced the birth and the death moves, as well as the no-dimensional change. It downgrade to the traditional sampling method. Each move has its probability to happen. And the birth move and the death move have the same probability, which guarantee the analytical solution of that Jacobian term. And the new model candidates will also be going through the Metropolis-Hastings acceptance rules, and we gather a series of samples across different dimensionality, and then we can infer the model property as well as the model complexity. Here I will show one example. One simple example is also a synthetical case of a 5-layer model, but only one logging point, so I draw it into a parallel layers form. The prior constraint is very relaxed. and we just constrain the number of layers and the model parameters in its broadened range according to its physics. The initial state of random samples is just randomly drawn from this prior constraint, and we studied the sampling process. We gathered the first plot shows the number of layers according to the sampling iterations, and it reflects the change according to the sampling. The model dimension changes along the sampling, and according to the histogram of those number of layers, we can have the statistics of those how many layers could be the best, could be the most possible one that to describe such a model, such a problem in target. And the samples we gather reflect more statistics of Earth model electrical properties, such as the histogram of possible model interfaces, the Z, one of our model parameter, as well as the heat map or the probability map of resistivity values. At a certain depth, the warmer color denotes the high possibility of the resistivity value could be. Those two statistical histogram maps of the figures are generated through the samples we gather across different dimensionality. And we can also draw the mean value or its maximum a posterior model, combine it through these samples. And to a multiple points, we use a benchmark model from SDAR 7-layer model interpretation, which is a 7-layer problem. And the logging tool drilling through it along a certain deep angle and across multiple layers, multiple formations. And the result shows at each logging point, we use the same schematic to infer the inverse interpretation or the mean value of those samples, and we gather those results into these two-dimensional figures. And at each logging point, we have these statistics, the histogram of the layer interface, that well the potential interface could be, and what is its probability, as well as the resistivity value. But the result may not be satisfying, because you can see a still inconsistent. The original figure is smooth, but the result is inconsistent. It is due to the insufficient sampling. So we still stress on the efficiency problem because we use a limited chain length, Markov chain length, but the samples we gather is not enough. So we need to use a new idea to boost such a sampling scheme. So we propose our last section here, which accelerates the traditional sampling method by using the tempering technique. To accelerate Bayesian inference, we have multiple ideas, like using multiple samplers running in parallel, because we always know the pains of the sampling methods is its low acceptance rate. We use the hybrid scheme to increase the sampling rate. And here, the transdimensional sampling largely decrease this acceptance rate due to the change of different dimensionality. So is there some way to draw samples in parallel or try to launch multiple Markov chain sampler at the same time? We have one example here. Without a good tuning, we use a random walk sampling method and launching 3 different samplers here to do the sampling work. Here's one very brief example. Without a good tuning, like the step size or the choice of your proposal, you still may suffer from the local problem. The sampler may sample from the local high correlated region and has very less dynamic to jump from this local high correlated region and sample from other region. So the combination of those samplers, the samples we gather, may not reflect the true distribution according to these multiple identical independent samplers. So we still need a way that to combine to adopting the multiple samplers, but with some communications. Before that, we need to introduce old story, and the story we mentioned before in the hybrid chapter. It is a way to connect the optimization problem with the probability function. Before that, I want to introduce any optimization problem to a dynamical energy system has its correlated form in the probability density function according to this. This one is unnormalized. You can add one constant to normalize this term and has its correlation, the relationship between the optimization here and its probability density function. So the global minimum of this optimization objective maximizes its probability density function. For a brief example, here we have a function here. Its correlated corresponding PDF has this form. It preserves the mode point as the local minimum, as the minimum point. So from the view of energies, we introduce one more variable here, the temperature T. The reason why we introduce a temperature T that to connect the optimization and its PDF is that T has a function that to modify the shape of this distribution. Here's one example, and the PDF of this function has a very long channel with very low probability. If a sampler wants to sample these two regions equally, it must need a very fine tuning and get this sampler to jump from these two regions. But it is very hard. So usually you're launching a random work sampler. The sampler will sample from one mode. The T changes the shape according to the form here. When the T equals to 1, it is the original distribution. With the increasing T, you can see the shape of this distribution change. It becomes more flattened. And once the T comes to the infinity, it becomes a flattened one, a totally flattened one. So temperature controlled prominence of local and global optima. The tempering form in the Bayesian posterior is very easy to just add by adding these power terms to modify the likelihood term and to modify the space of this likelihood function. The parallel tempering adopts these energy ideas from the perspective of energy. It by launching multiple MCMC samplers, all we call is a replica exchange MCMC. There are multiple chains running in different temperatures, but still need one running in the original form. So the chains at the original form, at the original temperature, sample the target distribution. And the multiple other samplers sampling from its tempered form or the more dynamical form, it has a better chance to jumping from different modes or different prominence in a certain distributions. The goodness of this tempering method is adopting the exchange or the random swap at each iteration between each randomly chosen chains. The advantage is that the states at higher temperature have a higher chance to sample in other regions or jump out from the local high correlated regions. So but the exchange between the chains may break the detailed balance. So we still need a Metropolis Hastings here, the rule here to guarantee the detailed balance of this gathered sampled. Using this sampling method, we do some other examples using the benchmark models. Here we introduce other models. Here is SDAR-A3 model with a 151 logging point. This is the result by a single chain, and we combine all the mean value of those samples. At each logging point, we run 8,000 iterations, which cost 40 seconds at each point. Here is a result refined by adopting the parallel tampering method using 16 parallel chains running in the parallel systems. And the result boosts quite much, and the inverse quality, the imaging quality, has been enhanced. But the time cost is still in the same magnitude and can achieve the real-time job because we're running the multiple chains in the parallel systems. The overhead is due to the communication or the chain swap at each iteration. And we can still find more statistics at a certain logging point. Here's one trace plot, and we monitor the posterior value in the logarithm form. And we can see here the tampering, the grayscale curves denotes the samplers, the trace plot in the tempered form. It has very large dynamics to jump from the different values according to the parameter space. But it has a chance to exchange with the hot chain or the sampler who sampled the original distributions. It gained much more dynamics and lead the chain to sample from a prominence, sample from optimal value here. And looking for the single points, still from that scheme, the right-hand side shows a very refined histogram, the probability histograms. And the left one, using only one single chain, has a very artificial thin layers, which is due to the insufficient sample. And we use the transdimensional ways to accommodate this method. And the value shows here due to result from the insufficient samples, which means that iteration needs much longer. And here is another example using the SDR 5-layer model here. Here is one thin layer, and the main target is beneath it. And it took about, for each logging point, it took about 20,000 iterations, and for 2.6 minutes approximately. We're launching 16 chains using the parallel tampering method, and the quality of this 2D model, the imaging result is quite enhanced pretty. And the time cost is almost the same, but the overhead, like I said, is due from the result from the exchange, the swap, and the communication between the chains. Okay, so next I will briefly discuss about our future work through 3 aspects. The first one is hierarchical Bayesian, and it raises us a question that how many prior we need, or how certain we have a prior. We have not stressed on this problem before because we define our prior in a very broad range. But how to make full advantage of the knowledge we know before, a hierarchical form might be one possible solution. It asks that the hierarchical modeling, Bayesian modeling, can be used when the information is available on the several different levels of the observations. The transdimensional way is one realization, which we put the k as a random variable, the number of our Earth model or the model complexity as a model. But we can still extend this Bayesian form in an infinite way, because we can extract the prior information of the prior and to take a full advantage, which can achieve a way of full data-driven sampling Bayesian inference. That is one interesting idea. Another way is we want to move on to the 2D transdimensional sampling problem. Because the current 2D inverse problem of the directional EM logging data is very slow, sometimes due to the forward modeling and the method we use, the very common parameterizing way to describe a 2D space is by using the mesh grid. But it is necessary. The 2D way is necessary for more challenging scenario like the fault and the pinch out. Such a way we cannot. There is still a bias between the 1D parameterizing. There's one example from a paper, and the 2D can resolve the fault property in a better quality here. A self-parameterizing way in 2D can be realized through the transdimensional sampling by using a new parameterizing way. Here we use the Voronoi cell to describe the target space, the parameter space. It might be a good way to reduce the number of dimensionality in the 2D space and to adopt the transdimensional way to infer the complexity of such kind of model. And the third possible direction, we could use the deep learning assisted inversions here. Although there are too many techniques, and we have ever tried that the forward and inverse modeling, it is a end-to-end model and is very suitable for the current end-to-end machine learning techniques. But so far yet, the end-to-end machine learning model has not yielded desiring outcome because we have less knowledge towards the physics behind it. So physical-driven process workflow has a bright future, I believe. There's one example in the recent paper shows that a combination of Bayesian sampling with the deep neural network, the GAN here, the generative adversarial networks, neural networks here, has a better performance combining the Bayesian sampling as well as the deep neural network. By sampling from the latent space, and the well-trained models can generate its response. It might be a good way to combine these two different techniques. To draw a conclusion in this presentations, we talk about the background and the current challenges of the ultra-deep service, that it has a very broad and extended range of the DOI. And we propose the statistical inverse framework that adopting the Bayesian inference to handle the local minima problem happened in the deterministic method. And to accommodate the low efficiency of sampling method, we propose a hybrid method and a tempering method to enhance the sampling efficiency and speed by adopting a hybrid scheme or the parallel computational system. And the self-parameterizing scheme was proposed that using transdimensional MCMC method, which is designed for the model complexity, for the inference of model complexities, which derive a Brighton ways to handle this model complexity inference. And to just conclude our work during this PhD period, we proposed the idea based on the frame of entire Bayesian inference. And our next step we can see is forwarding this such as a data-driven approach into the more machine learning or the more data-driven approach in the future. So that's all my dissertation and defense presentation. Thank you very much.
Give a hand.